Hello guys, welcome to my Physics 211 course project. In this project, our main topic is birefringence and how can we use it to determine the stress points of a plastic object like this plastic lid. We are doing this experiment in three stages. In the first stage, our goal is to investigate the Moses law and how linear polarization works with these lasers. For the first stage, we can do a quick demo. These are the linear polarizers, and as we can see, when they are parallel with each other, the intensity at the other side of the polarizers are at max, and when we change the rotation and make it perpendicular to each other, the intensity is almost at zero, which is as expected. And we took some data points, 11 data points for each rotation, and we did a scatter plot and compared with Moses law, as you can see in the screen. So we can say that first stage was pretty successful. In the second stage of this experiment, we are going to experiment with optically active solutions. In this case, we are going to experiment with sugar in water, sugar-water solution. Our argument is that sugar makes the molecule structure of the water asymmetric, and consequently the polarization of the light changes when it's being sent through this solution. Since I don't have this set up right now, I'm going to show a clip of it, and in this clip we can see that under cross polarization the light, the color that's absorbed from the top changes constantly when we change the rotation of the first polarizer. This is a proof that the rotation is proportional, let's say, is dependent on wavelength. So we can see that different wavelengths rotate differently, thus we observe different colors at the top. And in the third stage of the experiment, this is where we experiment with photoelasticity concept and how we can examine stress points on a plastic object. In this case, we're going to use this lid. We did a raster scan operation using this laser, and we took 11 by 9 sample points on this on a rectangular region using a stencil and this Arduino intensity sensor. After we acquired the data, we did an intensity map, as can be shown in the screen. This for the red laser and this for the green laser. I'm going to demonstrate a quick one here. As you can see, it's between cross polarization, and we can see a stress pattern on the object. There is a dark cross pattern. We can call this an isoconic fringe, and this is the same pattern that is observed in the data acquired from the raster scan, so they are consistent. I'm going to tell you more about the data here. As you can see, at the middle there is a high stress point where the fringes get at a higher density, so we can conclude that it's a internal stress point. It is also important to note that the isoconic fringes in this image, where the dark fringes appear, is caused by the external stress applied on the object, which results in an induced birefringence. When an object is under stress, the molecular structure of the material changes and it becomes a birefringent material, and the optical axis of that birefringent materials align with the stress direction. Thus, when the light is passing through two polarizers, it is blocked by the cross polarization. But to better show this, we are going to use a spoon and break it to show that it's really internal stress point. Also, additionally, we also took photos of the stress map of the plastic lid and filtered the red, blue, and green colors to better see the effect of wavelength and how how stress points are not dependent on wavelength. It's always the same for each wavelength. So when we observe the spoon under cross polarization, we can see that this point here is the internal stress point, and when I break the spoon, we can see that it's broken from right there. So it can be concluded that it's the stress point of the internal stress point of the object. Thank you for listening my Physics 211 course project. Thank you.